All right, hello, greetings. Let's take a look at exercise 3. So at 80 degrees C and 1.32 bar, the system methanol-ethanol is in vapor-liquid equilibrium. So we have a mixture of alcohols, methanol, and ethanol. So I'd expect component 1 to be the most volatile component, right? CH3OH versus CH3CH2OH, right? So component 1 should be the most volatile component, which follows our notation. All right, so methanol and ethanol is at vapor-liquid equilibrium at that temperature and that pressure. The composition of the two phases is such, right? And okay, y1's greater than x1, so it confirms component 1's the most volatile component. Calculate the fugacity and fugacity coefficient of each component in each phase. You may assume that the vapor phase is in the ideal gas state. Okay, got it. All right, so key here is we're told that we can assume that the vapor phase is in the ideal gas state. And so what that tells us is it tells us that the fugacity coefficient of component 1 in the vapor is equal to 1, and the fugacity coefficient of component 2 in the vapor phase is equal to 1. Okay. So if I wanted to calculate the fugacity of component 1 in the vapor, well, in general, that's just equal to Phi1V times Y1 times P. If I expand with respect to my ideal gas reference state, Phi1V is equal to 1, so it's just Y1 times P. Okay, and so F1V then is equal to Y1, which is 0.37 times P, which is 1.32 bar. Okay, so I'm going to put it on the next line so I can get it all to fit in. Okay, so F1V then, okay, plug it in and we'll calculate it in the next in MATLAB. F1V is equal to 0.37 times P, which is 1.32 bar. Okay, so I'm going to set everything up, and then I'll go ahead and I'll compute it. So that's F1V, F1 or F2V. Okay, likewise, if I were to expand, that would be Phi2V times Y2 times P. Phi2V is just equal to 1, so that's Y2 times P. Y2 is going to be 1 minus Y1. Okay, and so F2V then is going to be equal to 1 minus 0.37 times P, which is 1.32 bar. Cool. So I've got F1V, I have F2V. Now we also need to calculate the fugacity and fugacity coefficient of the liquid. Okay. Well, key is, I know I'm at vapor-liquid coexistence, right? So component 1's in both the vapor and liquid phase, where Y1's greater than X1. So I know I have two-phase coexistence. And so I know that the fugacity of component 1 in the liquid is just equal to the fugacity of component 1 in the vapor. And that's going to be this value that we were given up here, right? So I would compute that. Likewise, the fugacity of component 2 in the liquid is equal to the fugacity of component 2 in the vapor, and that's equal to that value I just computed here. Okay. But now it also asks for the fugacity coefficient, right? So in order to get the fugacity coefficient, well, if I were to expand out my fugacity, okay, I know that the fugacity of component 1 in the liquid, if I were likewise to expand the fugacity of component 1 in the liquid with respect to my ideal gas reference state or standard state, it would take the form of Phi1L times X1 times P. Right, my partial pressure is now X1 times P. Okay, Phi1L is my fugacity coefficient. We're told the vapor phase is an ideal gas. Okay, so Phi1V was just equal to 1. But we can't assume that the fugacity coefficient of the liquid is also equal to 1. Right, my liquid's not an ideal gas. If it was, I'd have F1V is equal to F1L, and if in both cases my fugacity coefficient's 1, then it must be that Y1 is equal to X1, right, which I don't have. Okay, so I know Phi1 isn't going to be equal to 1. Okay, so solving, okay, I'm going to end up with, so therefore, I end up with Phi1L is equal to F1L over X1P. Okay, and to simplify it, I said F1L was equal to F1V, where F1V was equal to Y1 times P. Okay, so this is equal to Y1 times P divided by X1 times P. Okay, so just to write it out here, so Phi1L, then P and P cancels, V1L is just equal to Y1 over X1. Okay. Likewise, and I'm going to comment at this in a second, if you do the same thing for component 2, okay, well that's V2L times X2 times P. So therefore, V2L is equal to F2L divided by X2 times P, where F2L, well, that was equal to Y2 times P divided by X2 times P. So I end up with V2L, P's cancel, it's just Y2 over X2. Okay. Now we'll compute values here in a second, okay? But here, component 1 is my most volatile component, so Y1 is greater than X1, so I'm going to get a phi then that's greater than 1. So the fugacity coefficient of component 1 in my liquid is greater than 1. Okay. Now remember, my fugacity coefficient is related to my residual Gibbs free energy, right? Specifically, RT log phi, okay, or let me just write log phi, right, of component 1 in my liquid. Well, that's going to be equal to 1 over RT times GR, right, of component 1 in my liquid. So if the fugacity coefficient is greater than 1, that means I'm going to end up with the residual Gibbs free energy of component 1 in my liquid that's greater than 1. Okay. Cool. Whereas in the gas phase, the residual Gibbs free energy was equal to 0. Okay. So the residual Gibbs free energy of component 1 is greater in my liquid than in my vapor, right? And this should really be my partial molar residual Gibbs free energy component 1 in the liquid is going to be greater than 1. Okay. It's 1, or the partial molar residual Gibbs free energy component 1 in my liquid is going to be greater than 0, okay, because phi1 is greater than 1. Or for the case of an ideal gas, the partial molar residual Gibbs free energy is equal to 0, right? And cool. So the partial molar residual Gibbs free energy is less in my vapor than in my liquid. So phi of my component 1 in the vapor is less than that of my liquid. And so my most volatile component, well, it's going to prefer the vapor phase, right, which corresponds to the phase with the lower fugacity coefficient or the smaller residual Gibbs free energy. Likewise, for component 2, I'm going to end up with X2 is greater than Y2. So phi2L is going to be less than 1. Okay, so phi2L is less than 1. Okay, I apply the same equation. I end up with the fugacity coefficient of component 2 in the liquid is less than 1. Or the partial molar residual Gibbs free energy of component 2 in the liquid is less than 0. Or in the gas phase, I have an ideal gas, right? It's equal to 0. So for the most volatile component, the partial molar residual Gibbs free energy of that component, my least volatile component, is less in the liquid than it is in the vapor. Fugacity coefficient, right, is less than that of the vapor. And that least volatile component, right, is going to prefer the liquid phase. Right? Cool. Okay. Cool how it all comes together. Now, if I want to compute some values, I've got MATLAB open up over here. So let's go ahead and let's compute it. Okay. So I'm just going to call this problem 2 just so I can save it, or problem 3. Okay, so problem 3. Okay, we're given y1 is equal to 0.37. X1 is equal to 0.25. Okay, so y2 is going to be 1 minus y1. I'm just going to go ahead and compute it. X2 is equal to 1 minus x1. Okay, so first we had f1v was equal to y1 times p. Okay, it's auto-completing on me. Well, it's because I need to define P. My pressure was 1.32 bars. So P in bars is 1.32. So F1V is equal to Y1 times my pressure in bars. F2V was equal to Y2 times P in bars. Okay. Fugacity coefficient was 1, so I don't need to worry about that. F2, F1, F1 in my liquid phase was just equal to fugacity component 1 in my vapor. F2 in my liquid was just equal to fugacity of component 2 in the vapor. and then to get my Fugacity coefficient, so Phi1 liquid was just equal to y1 divided by x1, and Phi2 of my liquid was just equal to y2 divided by x2. Okay, so if I save that and run, I can get all my values I can fill in. So F1V was 0.4884, 0.4884, and that's in bars. F2V, 0.8316, 0.8316 bars. Okay, my liquid, so it's going to be equal to my vapor, so this is 0.4884 bars. This is 0.8316 bars. Fugacity coefficient of component 1, 1.48. Okay, that's dimensionless. And Phi2 is 0.84. Okay, and again, right, just so right here, Phi1 vapor was equal to 1. So the Fugacity coefficient of component 1 in the liquid is greater than that in the vapor, or equivalently then the partial mole of residual Gibbs free energy of component 1 in the liquid is greater than that in the vapor. Okay, so my most volatile component, well, it prefers, right, the vapor phase, right? It's the component with a greater propensity for the vapor. Hey, and so my Fugacity coefficient of component 1 is greater in the vapor than the liquid. For component 2, okay, and remember, just right here, Phi2V, right, is equal to 1. So I find that for component 2, the Fugacity coefficient of my liquid is less than that of my vapor. This is my least volatile component, which means the partial mole of residual Gibbs free energy of component 2 in the liquid is less than that of my vapor, right? And my least volatile component, right, has that greater propensity to be in the liquid phase, right? Cool. So there's my calculations, right? There's some cool physical insight I can get. Everything makes sense. Everything is great. Now, just for completeness, since we kind of talked about this in class, if I were to assume that this system also obeys Raoult's law, okay, so let me just, this is going above and beyond. If I assume that my system obeys Raoult's law, well, so if I have my isofugacity equation, okay, and so if I have a system that obeys Raoult's law, when it comes to my vapor phase, right, I assume my vapor phase is an ideal gas. When it comes to my liquid phase, I assume that my liquid phase is ideal, that pure component at saturation at T, that's also an ideal gas, and my Poynting correction is negligible. Okay, when I do that, okay, then my liquid phase fugacity takes the form of x1 times p1 sat. Okay, cool, right? And this, again, is just equal to my fugacity, which I'll write here is the fugacity of component 1 of my vapor. Okay, all right. Now, here I have a mixture of chemically similar compounds, all right, methanol and ethanol, so it should be reasonable to assume that it's an ideal solution. We're operating at low pressures, so assuming vapor phase is an ideal gas, right, for that pure component at saturation is reasonable, especially since we said that that mixture, the vapor phase, could be assumed an ideal gas. And operating at low pressures, right, should be reasonable to assume my Poynting correction is negligible. Okay, and so let's just see here. So if I wanted to, right, I could solve for P1 sat. So P1 sat, right, is then going to be equal to y1 times P divided by x1. Okay, cool. And so, I could use that as an estimate of my saturation pressure of component 1 at 80 degrees C, okay, of methanol, right, should be given by this. Pretty cool. Okay, but yeah, so you can in theory calculate P1 sat, and then likewise I could calculate P2 sat, all right, from the data given. So P2 sat would be y2 times P divided by x2, all right, and hey, if I want to get really cool and nerdy, all right, y1 and x1, all right, we said was equal to phi1. Okay, so P1 sat is essentially phi1L times P is another way I can write it. And likewise, this would be phi2L times P. Okay. But all right, that's going kind of beyond. But just a note, right? If I wanted to, I could calculate it as such. So P1 sat, so Phi1L, right, that was greater than 1. So I end up with a P1 sat that's greater than P, and a P2 sat that's less than P, right, which also checks and makes sense. Hope that helps. If you have any questions, by all means, let me know.